implementation of pyCUDA, and Aditya will be presenting that. Aditya is a computer geek. He loves Python. His focus areas are parallel programming, compilers for multi-code processes. He programs for fun, develops search engines, websites. Currently working for Dirt9. Yeah, welcome.
Thank you. Hello everyone. Hi. Good afternoon everyone. I'm Aditya. Today I'm going to talk about implementation of pyCUDA. So this is basically my Twitter ID and this is my about me ID. So today's talk will be focusing on introduction to CUDA and extensions for Python. Basically, if you have a new libraries kicking in for C or C++ and you want to integrate it to Python, so the method you will be using is development of extensions, and we will be talking about Boost Python, CodePy and pyCUDA. So basically, CUDA is a parallel processing computing platform and a programming model. Basically, what CUDA does is it implements the algorithm in graphic processing units. Basically, GPUs are used for high-end gamings. Most probably, all of your laptops will be having one, either it from NVIDIA or AMD. So, CUDA is proprietary of NVIDIA. So, my focus is on CUDA because basically my graphic card is NVIDIA. So, I worked on it for around 3 years, and it's really fun working on it. And it is a ever-developing platform for parallel processing. So I want to focus on the programming model here. So it is basically SIMD. The recent graphic cards are having MIMD. So what SIMD is, single instruction, multiple data. What it means is the process stack will be having, suppose it contains 4 assembly code, then different data will be executed at the same time with only those 4 assembly lines. So this is basically what SIMD is. And coming to MIMD, it is basically implemented for Kepler architecture for NVIDIA cards. I don't know about AMD. So MIMD is multiple instruction, multiple data. The basic disadvantages in SIMD is you can execute even it is you are using 10 threads or 20 threads or 30 threads. The other threads will be in rest. They will not be used by any of the algorithms or any of the process. This is the main defect of SIMD. And the new MIMD architecture, what it does is, if there are any threads which are not active, the CPU will ask those threads to execute certain tasks. So basically you will be implementing 2 codes at the same time, and those 2 codes are parallel codes. The next one is the programming model also contains the separate memories for threads, blocks and grids. So basically a GPU divides itself into, it has millions of threads basically. It divides into grids, and grids are in turn divided into blocks and in turn into threads. Threads are the very basic elements which basically does the computing. So each thread has its own separate local memory. I'm talking about CUDA. This is not an OpenCL, so the mapping will be almost same, but the terms are different. That's it. The concept is almost same, but the terms are different. So threads will be having their local memory, and the latency of accessing this memory is very less. So when it goes to blocks are multiple threads. So my GPU is NVIDIA 240M. It contains 512 threads, and I can execute 512 blocks. So basically what is, each block contains a maximum of 512 threads, and I can have such 512 number of blocks and 32 number of grids. So each thread has its own local memory. Each block has its own shared memory. The grids share the global memory. Sorry. Coming to next slide. Yeah, this is the basic workflow if you want to do high performance computing on using CUDA or OpenCL, or recently Intel has released Intel Xeon processor, so coprocessor. So basically the idea is basically the same. First, you allocate the memory on the GPU. Next, you copy the data from CPU to GPU. Next, you initiate the threads, blocks, and number of grids you want to run on the GPU, and you call the kernel that runs on the GPU, and then copy back data to CPU, and then you have to free the memory on the GPU. So basically, here this is a very simple architecture. Why we are copying data from CPU to GPU, and why we are initializing the threads and calling the kernel from the CPU. This is the main question what I have got when I started using CUDA. The problem with the GPU is that they can't create their own work. Basically, if you are running a program in a CPU, what we are doing is the CPU itself builds its own stack instructions to the stack, but the GPU can't do that. It can't get the instruction sets of its own into the stack memory. What here we will be doing is we'll take the help of CPU to give these instructions to GPU, so that these will be executed on the GPU. And after the work is done, we will transfer it to the CPU and we will free the memory. The main problem with GPUs is that we will be communicating to GPU through PCI Express bus. The memory transfer from CPU to GPU may seem very high by seeing the numbers, but basically it is the main bottleneck for high performance computing. The GPUs are so fast, so why is this bottleneck? I want to talk to that about. In CPUs, we do it very quickly, but in GPUs we take a lot of help from other threads and we do it slowly, so that we can get maximum performance from all these multiple threads. So yeah, the PCI Express bus. I'm sorry. Copying the data. In the GPUs there are millions of threads, but the accessing of the memory the memory by the processors is very low. The speed by looking at the numbers, it will be very high, but as there are millions of threads working at the same time, the memory speed is not up to the mark, so that they can get the memory in time to perform the execution. So let's get to the real stuff here. Is writing extensions simple? Have anyone here wrote an extension here for Python? Very few members. So basically, what extensions does is we love Python, but there are some libraries in C++ which we really want to use, and we want to integrate them to Python. So we build these extensions and we'll importing them into Python. Writing extension is simple, but it's very hard. Python is nothing. An extension is nothing but a shared memory .so or .dll. For writing an extension, these are the 4 important things you need. One is basically the header file python.h. The next one is C functions you want to expose to the Python, and the table mapping and the initialization functions. So this is the code for getting the sum of numbers from a list. This is the extensions. This is the extension code. The first one here. Yeah. The first function, the first method is a function what we want the Python to execute. So here we are initializing a method which returns a static PyObject reference. So basically, most of the data types in extensions are Python objects. Here we are initializing list object and value object, and we are calculating the sum of list object, and by transferring each value into the value object and adding it to the summer here. So the basic, there are 3 points to be considered for writing an extension. The first one is the data types. The arguments you are giving to the functions, you should be taking care of whether it's a list or a dictionary or a single integer or a float, because in C they will only consider what the data type it is, whereas in Python you can just add anything to a list. Yeah, and another thing is error checking. The exceptions, first I wrote extensions. It is very difficult for me because there are lots of errors, exceptions basically. So the first thing we need to consider is find out where the exceptions may occur, and we have to make the error checking. So here it is, we are using pyarg parse tuple. Here we are checking whether it is initiated or not, list object is initiated or not. If it is not initiated, it returns null and this function gets exited. So in this line we will be taking the size of the list object, and we are assigning it to one other variable, and we are adding it to the sum. So basically sum is a long, you can see here. So pyint as long is used for typecasting, and we are returning pybuild value. So this is important for, if you want to return a value, you have to use pybuild value, and here you can see in quotations is L. L means long, D means int, F means float, and the return type and the return variable is sum. So and another thing is you have to focus in writing extension is this object you are assigning. There is reference counting. There is reference counting here. Reference counting is if you are assigning one object to other, the reference count of that number get increased, and this is done by Python itself. So when the count comes to 0, it gets deleted. This is the basic memory management, how it works. If you are using a value and you are assigning into other, its reference value increases. If you delete the parent one, the child will get deleted also. So this function is a method definition function. This is the name of the method, meth varargs. It means that we are passing some arguments into the function, and this is basically addition a list of values is basically just works like a doc. PyMod init function, what it does is it initializes the method when it got imported to Python. So we are using here myMath method args. myMath is what you type, so that it is the name of the extension. myMath is the name of the extension. Math methods is basically this one, and you are importing this one, and the math sum you are importing this method also. So next we are going to boost Python. So what is boost Python? Basically writing an extension is really a pain. So using boost Python, it will be very easy. You don't have to consider reference counting, data types, and reference counting. So what boost Python does is it quickly and seamlessly expose C++ classes and functions and objects to Python, and the code is very simple. You don't have to care about reference counting. You can use STL for this one, whereas for building Python, Python extensions, raw Python extensions, it is very difficult. It supports C and C, different C and C++ APIs. So first I write a CUDA code a lot, and once I thought, why don't I write an extension for Python, so it will be very useful. But seeing this code, I was very much terrified by that. So after a lot of search in Stack Overflow, I have found that Boost Python is very good one. So this is basically a Boost Python code. What you need to do is you just compile it, build a shared library, and you have to import it to Python. So basically the micro here, Boost Python module, what it does is it initializes initialization function and method definition functions, and the pycon_ext is the name of the extensions you will be importing into the Python, and greet here is the name of the method you will be using in Python, and greet here is this function. So if you run this one in Python, you will be getting hello PyCon India. So what is CodePy? CodePy is a meta programming toolkit for Python. It uses Boost Python, extending Python at runtime. When I thought of writing an extension, CUDA extension to Python, I have very much successful using Boost Python. But what if a person want to write his own algorithm? So it is very difficult for anyone to write his own extension and again importing it into Python. So CodePy, it creates the extension at runtime and it imports that extension on the go. So it is CodePy is written in Python by Andreas, and I am very thankful to him. So what is metaprogramming? Here metaprogramming means a Python code creates a C file, and this C file gets compiled, a shared library is built, and it is imported into Python. So this is a CodePy architecture here. So the second block here, extension module code.compile. So what it does is, you can see the code here. This code will be sent to CodePy generate source code. This is a cgen package which is a part of CodePy, and which is initially a part of CodePy, and now it has become an independent package. So this cgen will create a C file which is a Boost, which contains Boost Python libraries. Means basically a code which look like this. So, and again it compiles and it creates a shared library here, and it gets imported here. So you can use that function and you can go on using that one. So this is basically the code for CodePy. So here it is cgen, which means it creates the C code. CodePy.bpl, which means you have to use Boost Python module. We are initializing Boost Python here. Adding to preamble means it basically includes the header files here. You can see the pink statements here. Those are basically C commands. And one heads up for this one is the block here means there is a curly braces here. It is analogous to curly braces in Python. And coming to JIT means everyone knows it's just-in-time compiler. Guess_toolchain. What it does is it guesses the compilers we have, and it compiles based on this. So if I am using pyCUDA, it go for NVCC. If I am just using C libraries, it will go for GCC. So here I am using compile guess toolchain, and I am initiating an list and I am using it. So this is what basically I have done, what I have told. Initializing body means basically this function body, add function, and mod body means function body. So RTCG, it's runtime code generation. So as I have told you, CodePy creates extensions on the go. So it's basically you just write this code and you compile, you just run it in Python and you will just have a extension. So you can see here it is print sum a. It is here. It is the function here. So pyCUDA. So what's great about pyCUDA is it maps all CUDA into Python. Added robustness. It is very convenient, yes, because we are using it with Python, and it's very fast. So this is the architecture of pyCUDA. So what it does is, yeah, let me start with this. So in this code, we are importing from this library, and float a. This sentence means these are the arguments of the kernel functions in CUDA, and this is the algorithm what we want to execute in it, and linear underscore combination is the name of the method we are implementing here. So this is basically a device code, means there are two parameters here. Underscore global underscore means it is basically which can be executed from CPU code, and device underscore device means it is executed on the GPU, but it is called from another global function. So pyCUDA module GPU array, basically you can see here element wise kernel, it is shown here, and you will be using it. This code will be converted into a good function with Boost Python extensions used in it, and it is you can see here Boost Python extensions, and it is compiled and imported into Python on the go. So this is the pyCUDA code. So here you can see memory underscore allocation, which means you will be allocating the memory in the GPU, and memcopy, it copies the data from CPU to GPU, and you can also here NumPy you are using NumPy here. It's you know about this library. It is used for scientific computing, and this is the function you will be calling here. W5 you can see here also, and you are calling this function a with, this is the argument a underscore GPU, and this is the block 4, 4, 1. So it basically has 4 threads, 4 x-dimensional threads and 4 y-dimensional threads, and you are again copying it to host. So this is how pyCUDA works. You edit the code, you run it, and the GPU, here you can see source module. The code here from goes to here. Whether this code is cached or not, it will check it, and if it is not, it is compiled, and a GPU binary called as cubebin is created, and it is sent to GPU, and it is run on GPU. So summarizing it, building Python is very hard, and Boost Python really simplifies it, and CodePy generates C++ code and build extensions at runtime. pyCUDA it uses CodePy and CUDA to run high performance computing using Python. Thank you.
Do you have any questions? Anyone?
Yeah. Yeah. Yeah, it's your preference. You can use C++ or C. Most preferably, you can use. I recommend is using C++ because have you heard about Thrust? Thrust is a CUDA library. It's basically for it look like C++ STL. So if you are, I recommend it using Thrust and STL libraries because they are very easy to work. Yeah, you can just, this is basically a comment, right, in this one source module. You're talking about this one only, right? This one. Yeah, actually, this one works backend. Okay, this is a pyCUDA code, and this one is related to element-wise kernel here. You can see here. You are using this one for running pyCUDA. You will be using source module, but in backend it will be using element-wise kernel if you have more than 2 functions to implement on GPU. Okay. 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 Yeah. Yeah. Okay. Okay. Yeah. Yeah. In a single word, the answer is no. But there is a difference between CPU code and GPU code. Basically, in CPU, you will be serializing every code. Suppose a summation takes is faster in CPU than in GPU. The reason is the clock speed of GPUs are around 800 megahertz. Okay, the basic means economical GPU has 800 megahertz, whereas a good CPU has around 3 gigahertz. So summation means you will be just accumulating a number in the stack. That's it, right? So it will take. It depends on number of cycles. So in one cycle it will add, next cycle it will add. So for serialized algorithms, I prefer not to go to GPU. If you have something like matrix multiplication, something related to matrices, going to GPU is a very good idea. But the talk is about giving you that feel of high performance computing in Python. Okay. And I also want to add one more point. There is another library called Copperhead. It's built by Brian of Berkeley. It's a very good extension for Python. What it uses, it uses a decorator so that you don't need to write this C++ or C code. Basically, you can use the Python syntax to implement high performance computing in the newer system. Okay, thank you. Any more questions? Yeah, sure. No, actually, Boost Python is developed by guys from Boost. Yeah. So CodePy is built by Andreas. What it does is, you just need to map. In this one, you just need to map the C code. So you will be just implementing. You don't need to go for learning into Boost also. So Boost document is good, but it's not recommendable for a beginner. Okay. So using this one, it is just basically a C++ code. So you can just write it, and if you want the feel of Python and you want to implement it, this is very good. Thank you. Thank you, everyone.